And here we are with the last packet of Unit 9. So this is RC Circuits Day 2. So we're starting off with this example, Circuit A, Circuit B, what must be true if the voltmeters read 0. We had kind of a formula for this before. For Circuit A, with the capacitors, it was that C1 times C4, right? The diagonals times each other, is C2 times C3. So if you plug in your values, right, this is 4, C4, that's what we're looking for, and this is 3 times 8. So C4 ends up being 6 microfarad. These are all microfarad, right? And then for B, it was the same kind of thing, right? The diagonals R1 times R4 is R2 times R3. The product of the diagonals should be the same. And so what we end up with here, plug in the numbers, so it's 4 times R4 is 5 times 20. It's 100 divided by 4 gives you 25. These are all just regular ohms. Okay, but now what about example 2? In example 2, we've got kind of a new situation. We've got 2 capacitors and 2 resistors. Okay, so let's label these correctly. R1, R2, we'll call this C2, and C1. So what are some things that we know? We know that the potential on capacitor 1 is equal to the potential on resistor 1. These both have to be using up the same potential difference, right? And then the voltage on capacitor 2 has to be equal to the voltage on resistor 2. Because these 2 capacitors are in series, I know that Q2 is equal to Q1. And because these 2 are in series, I know that I2 is equal to I1. This is for the capacitors. This is for the resistors. Okay. Now, V is given by, for capacitors, Q over C. Okay, so this is Q1 over C1 is equal to, now V is given by IR, right? So this is going to be I times R1, I times R1, and the same thing is true for, and this charge is the same here, so that could be just the same. And then Q over C2 is equal to I times R2. Okay, and so these I's are the same, so I can kind of solve these here. So this I would be Q over R1 C1 is equal to Q over R2 C2. But the charge is the same also, right? So these cancel out. So now R2 C2 is equal to R1 C1. So we end up with this kind of thing. And now notice this is different. This is not the product of the diagonals. It's the product of, the 2 top ones equals the product of the 2 bottom components. Okay, now let's take a look at example 3. Before, when we were looking at RC circuits, like in the part 1 packet, we had things charging to, either 0. The current was always going to 0. It was either charging or discharging. But in this case, in example 3, we now have a little bit more of a complicated circuit. And so over time, notice the current can bypass the capacitor. So if this capacitor gets totally charged up, there will still be current going this way. But our principle still works. Initially, the capacitor acts like a wire. So when this switch is first closed, all of the current will go through here. The current will bypass this because current would rather go through a wire than through a resistor. So this acts like a wire. And then after a long time, this is like an open switch. So after a long time, the current is going through here. And there's 0 current effectively through this. Okay. So what is the question asking about? It says, what is the current? So at time 0, what is the current in R1 and R2? So at t equals 0, the current going here through R2 is 0. All right, so that's the answer to question B, I think. The current through R2 is 0. Okay, so that means that all of the current initially will be going through R1, which is 20 kilo ohms. So the current through there will be V over R, which is 30 volts over 20 kilo ohms. So that's 1.5 milliamps. And then C asks, what is the current in resistor 2 a long time after? Right. So now a long time after, this is like an open switch, all the current is going through here. So the current a long time later will be V over R1 plus R2, because now I have current going through these two resistors that are in series. And this is how I get the effective, the total resistance for those two. And so this ends up being 30 volts over 30 times 10 to the third ohms. So this ends up being 1 milliamp. That's 20. This is 10 kilo ohms. Okay. Now we have an extension question. What is the voltage across the capacitor a long time later? Right. So VC as time goes to infinity. Well, quick way to answer this. The voltage across this has to be the voltage across this resistor. These two things are in parallel with each other, right? If this is the plus, the minus side, the plus, the minus side of the resistor, plus, minus side of capacitor. If you go from one end of the resistor to one end of the capacitor, you get the same charge, plus to plus, minus to minus. These two are in parallel. So the voltage across this here is R, IR. So here's I, here's R. So 1 milliamp times 10 kilo ohms would give you 10 volts. So if there's 10 volts across this, there's got to be 10 volts across this a long time later. Okay, and that means then there would be 20 volts across that resistor. Let's take a look at example 4. This one is the same basic setup except for changing some of the numbers. R1, R2. Okay, so when we're solving this problem, we have to realize is that the voltage that collects on this is going to be the same as the voltage across this resistor. And so in order to get the voltage across this resistor, I need to find the current. And so the current a long time after this has been closed is going to be 20 volts over 35 kilo ohms. So this is going to be 5.7 times 10 to the negative 4 amps. All right, so if that's the current, I can multiply that by R2, and that gives me the voltage across this. Right, so that V on R2 a long time later is going to be V times C, which is 8.57 volts. So that's how much voltage now is being discharged across this. Okay, and so the current, now when it's discharging, the current on R2 is going to be given by the voltage on the capacitor as it's decreasing divided by R2. So V on the capacitor, which is equal to the voltage on R2, divided by R2 times e to the negative t over tau. All right, now when I go to find the time constant, I find that the time constant is 4 times 10 to the negative third seconds. That is also the time t that we're asking for in this. And so this ends up just being negative 1. So VC is 8.57 over, and then this is 15 kilo ohms times e to the negative 1. And what is that going to give us? It gives me 2.1 times 10 to the negative 4 amps. Okay. Or, I mean, the other thing I can do, since I know it's one time constant, I can find what the voltage is. I can find 37% of the voltage and then divide that by 15 kiloohms, and that'll give me the same thing. So I started filling this out, but I realized as I look at the questions, I don't even need these numbers. The only thing I really need here is 12 volts, because whatever is happening here, I know that this is going to have 12 volts across it, and this thing, this combination, will have 12 volts across it as well. And the voltage on this is going to be following this. So the voltage on the capacitor is the EMF on the battery, 12 volts, and this is increasing, right? So 1 minus e to the negative t over tau. And then this wants to know what are the potential difference across R1 and R2. All right, so why don't we just solve this quickly, because this is going to be 12, 1 minus e to the negative. Now t here is 2 tau over tau, right? So that simplifies to just e to the negative 2. So 12 times 1 minus e to the negative 2, and that gives me 10.4 volts, right? That's going up as time goes on. For B wants to know what is the potential difference across this one, right, R2. Well, V across R2 is 12 volts. That's the same. That's staying the same the whole time. And the potential difference across this resistor is decreasing. As the potential difference across this increases, the potential difference across this decreases. And that would be according to 12 times e to the negative t over tau. But since I know the potential difference across the capacitor is 10.4, that means the potential difference across R1 has got to be 1.6 volts, because these two have to add up to a potential difference of total of 12 volts. And that's it. And then example 6 is one of the homework problems. Actually, it's number 65 out of the text. And you can see the textbook solution for that, which is on Haiku. And that is it for Unit 9.